Okay, so today it's our honor to invite Professor Phillips, who received his bachelor's degree from Urbana College and his PhD degree from University of Washington. And so he'll give us two talks. The first talk is about the quadratic fixed point for superconductivity and modulus. Thank you.
Thank you. Yes, I'm going to talk about something which I think is exact and rigorous. Since that seems to be in the air.
Except unlike things that I talked about, which are neither exact.
That's right. Where do I have this thing going? Not exact, rigorous. Neither. Okay, so my collaborators are two students, Luke Yale and Jin Chao Zhao, who is right here, and a math colleague of mine, Gabriele Lanave, and a postdoc, Edwin Huang, who is moving off to Notre Dame. Now, for those of us who grew up in scientifically in the 80s, it's sort of strange that this conference, which is entitled Fractionalization, Criticality, Unconventional Quantum Materials, hasn't really focused on the cuprates yet. This is not an accident, as you will see. Okay. Sorry, what did I do?
You flashed out the screen, it's one at the top or bottom.
I don't quite know how to use this.
Let's probably go to the right.
Right? Okay, right. Okay, so just go to the right.
Yeah.
Is that right? You know, I'm just going to do this because I know this works. Yeah, okay. The Mott problem. Okay, so the Mott problem is the fact that you have a half-filled band, but it doesn't conduct. And that problem defined the 80s. Phil Anderson, that was the problem. And this problem was viewed as having all of these things in it. And it is paramount to solving this problem, the cuprate problem. And in the context of this problem, many scenarios have been proposed. And here are just some of them. I just made this list yesterday. And there is no rigorous theory of any of this. But there is one thing that we do know. These systems are doped Mott insulators. So all you have to do is solve the Hubbard model. And you have to solve the Hubbard model in 2D. You can't do that. The best you can do is look at what numerical simulations are telling you. And regardless of what order you might think is relevant, there are two features which appear in simulations of the Hubbard model. The key one is that if you look at the non-interacting band, this non-interacting band, in the presence of Hubbard interactions, on-site repulsions, splits into two pieces. So each K-state, which is right here, now has spectral weight both at high energies and at low energies. And this gives rise to non-trivial physics. It also breaks Fermi liquid theory, because now there's a 1-to-2 correspondence as opposed to a 1-to-1. Now that's what I'm going to focus on. And because you have spectral weight both at high energies and at low energies, if you were to integrate then the spectral function over the frequency, you will obtain one sign up to here, another sign up to here, and hence you can get this thing called zeros. So the real parts of the green function will in fact go to 0.
I'm sorry.
With the reshare.
Yeah.
Oh, it's not shared?
Yeah, there are some problems with the webinar.
Has to be done.
Probably we need to.
Oh, sorry. It's because we clicked away.
This should be this one, right?
Yeah. The desktop share. Okay, so now it's sharing.
Do you want to?
And then I'll go into this.
Why don't you hide the
Oh yeah.
See, if you hide that, I think you have to go and do a reshare.
Oh, really?
No.
You can hide that stuff.
But we don't have the clicker. How can we get the clicker?
Well, no, it's fine. I'll just do this.
Oh, okay. Sure.
That was causing the problem.
Sorry about it.
Okay, so let me just go over here. You have zeros. Okay, so now this is well known, but it's hard to do. And it has partially paralyzed the field. And then what you have to do is go and you can go and illustrate the Cooper instability with this as your background in 2D for the Hubbard model. Okay, so that can't be done. So the question I asked is what next can be done? Okay, now a very famous debate, is there a simpler approach which captures this feature of the bifurcation of the spectral weight, zeros, etc. Okay, now this field was paralyzed by a debate between two very famous people, Bob Laughlin, let me just put them both up, and Phil Anderson. And this obvious thing which comes out of the simulations is the very thing that Bob Laughlin noted there is no real understanding of. And he excoriates the field exactly for this, because if you can't precisely discern what are the excitations which give rise to the lower or the upper Hubbard band, then what are you really talking about? And as a result, he opted for mean field theory. You split the spectrum into two bands, you break the Brillouin zone in half, you've gotten rid of the Mott problem. So for Bob, there is no Mott problem, there's just a Hartree-Fock calculation. Okay, and on some level, part of the reason why there is no representation of Cooper physics here is because of this. A lot of people are doing Hartree-Fock. You look at the Mott problem, that's what everyone's doing. And it's because of this paper, at least in my understanding of that. And Phil Anderson said, look, this is absolutely crazy. And let me just underline the key statement here. He said, it's the tragedy of Mott that although he almost certainly won his Nobel Prize for the Mott insulator, Slater couldn't think clearly about finite temperature won the publicity battle, which is the reason why there's so much Hartree-Fock going on. Okay, now the issue is that if you start with a non-interacting band, you have to show that there's a gap. So you break the spectral weight per K into two different energy states. Okay, and that's not trivial. What you'd like to do is come up with a way of doing that that allows you to go and do calculations. And if you do that, there's no way of putting this back together again. Hopefully that will be continuously related to the Hubbard model. Okay. So that is what I want to focus on. So what is the minimal model for Hubbard bands? And if you do have such a model, are there any relevant perturbations? And if there are no relevant perturbations, can you show that somehow this defines a stable fixed point? Okay, so that's the goal. And so let's start with something we all understand well. Let's look at Fermi liquid theory and look at the instabilities of this. And this is just your favorite paper. It's either Polchinski or Shankar. It's probably closer to Polchinski. So you look at a Fermi surface, and K represents momentum along the surface. L is perpendicular. And you want to scale towards the Fermi surface. So I want S, the scaling parameter, to go to 0. So I'm preserving the Fermi surface. If you do that, you find that any local interaction that you add, regardless of its sign, will have either a positive scaling dimension or it will be marginal. The chemical potential, though, will have scaling dimension -1. That just means it's a relevant perturbation. It doesn't take you away from anything, but helps define where the physics is. So that's well understood. So there are two things. As long as you're in the thermodynamic limit, you have local interactions, you have a spherical Fermi surface, you're done. There's nothing you can do except superconductivity or a charge density wave. Okay? So what this means is that if you look at Fermi liquid theory, and I've written it just simply here, and you add in any local interaction, you flow to the Fermi liquid fixed point. The only thing that takes you away from there is BCS, is this pairing interaction. These are the momenta. And you find you have a BCS superconductor. So that is well understood. Let me just be more pedantic about this. If you define the beta function in terms of this parameter G, you find it goes like this. And so there's only runaway to strong coupling when in fact momenta are opposite sides and the interaction G is negative. Sorry, G is positive, so this minus sign preserves this. Okay, now let me just focus for a minute on what this interaction really looks like in real space. It's completely non-local in real space. It's all the pairs interacting. So it takes something which is non-local in real space to break a Fermi liquid because Fermi liquids are completely tangled in real space. It's band structure. There's nothing local that can destroy that. And you form this gap right here at the chemical potential. Okay, so you look at Fermi liquids.
Sorry, that non-locality is artificial.
It's
Even
exact.
if you start with it, no, it's incorrect. It's a mean field statement. In mean field theory, you write on a pairing Hamiltonian, and it's true that if you take it literally, it's non-local in real space. But you evolve into that if you have a suitable attractive interaction, which still has locality in real space. It's a question of whether the starting point of the flow is. If you begin at the Fermi surface, it formally looks non-local because by the time you essentially project it into.
So that's where I'm beginning, and that's where the argument is. So your point stands, okay? But that's where the argument is. That's where that's where the theory is. It's on the Fermi surface, okay? And okay, so Fermi liquids have K as a valid quantum number. You look at the beta function for local interaction at 0, this thing diverges. Okay, now the question I want to ask is, if you're trying to describe the cuprates, which aren't Fermi liquids, you clearly have to go and solve this problem from a completely different fixed point. And can you formulate such a fixed point? Can you say anything about it? And can you do any calculation? Okay, another way of stating this is, can you find an operator whose scaling dimension is more negative than -1? And if you can that somehow describe this splitting of the spectral weight into two pieces? Okay, so Fermi liquids are very simple. They have doubly occupied states all the way up to the chemical potential. So the simplest way of getting a non-Fermi liquid would be somehow if you added some operator that gave rise to single occupancy below the chemical potential. That would clearly be a non-Fermi liquid. Now you want to do so preserving time reversal symmetry. There's an easy way of doing that if you don't preserve that. Okay, now there's another thing which comes into non-Fermi liquids, and Phil Anderson is the one who kept harping on this, that the spectrum for particle removal and addition is not symmetrical around this point. If you look at this part is different from this part. So right around 0 energy, the locus of points there, you find that it doesn't look the same. There's this particle hole asymmetry. Many of you have heard of this, and here is Phil Anderson in his last words, that he's baffled by the almost refusal of theorists to confront this particle hole asymmetry head on. Okay, so Phil Anderson doesn't need any advertisement, but this talk kind of looks like one for him. But anyway, I think he is certainly right about these things. Okay, and if you look at other materials, it's the same thing. There's this particle-hole asymmetry. Okay, so if the simplest way of getting a non-Fermi liquid is to have single occupants below the chemical potential, and we know we need to have particle-hole asymmetry, the question I ask is, are these two things related? And is that somehow related to this issue of the splintering of the spectral weight into lower and upper Hubbard bands? Okay, so what I want to do is take a closer look. Forgot about this. Another paper by Anderson. This is one by Haldane. They probably weren't the first to say this, but they're the ones that I read where I finally understood this point. Okay, so I want to write the Hamiltonian for a Fermi liquid in the spinor notation, where psi p is this two-component spinor. Okay, now what this does is that it shows you that even in the charge sector, there's an effective SU2 symmetry. So there are four objects here in these spinors, here and here. And their point is that if there are four objects, the rotation group for a Fermi liquid is really O4. And if it's O4, there are two very simple subgroups here. One's SO4, which is the fact that both the spin and the charge degrees of freedom have an SU2. That's SU2 cross SU2. And these are characterized by a matrix, a rotation matrix, whose determinant is 1. And over here, there's a determinant of -1. This subgroup here is the quotient of O4 with SO4, which is just Z2. Okay, now what is this extra Z2 symmetry that Fermi liquids have? Okay, so that was really the point of their paper, and I dropped the minus sign since we have time reversal symmetry. So what I want to do is take these four operators and construct the real version of those. So I go to the Majorana basis. But I take linear combinations of them, and now I can apply the improper rotation to these, and you can see exactly what the Z2 symmetry is telling you. So if I look at this, at the matrix now, the one that has to do with improper rotations has 1 minus sign. It just has to have an odd number. The simplest one has 1 minus sign. Let's apply this to this. You apply that to this, what you find is you're mapping this into this. So that is a particle-hole transformation. It's this transformation. Okay, so when does this Fermi liquid Hamiltonian have this Z2 symmetry? Well, it's only true if the Hamiltonian is equal to 0, which means it's only true for electrons right at the Fermi surface, right at the chemical potential. At that point, you can map the creation and annihilation operators for one of the species onto one another. Remember, you want a minus sign, so it's really just one of them that you're doing. Okay? At that point, you can make this transformation with impunity. Nothing changes. Okay, so that's this particle-hole symmetry that is present in Fermi liquids. And it's the Z2 symmetry in momentum space. But it's just restricted to stuff right at the Fermi surface. Okay, so how do you destroy Fermi liquids then? You just destroy the Z2 symmetry. So if I look at the Hamiltonian for a Fermi liquid, I'm just writing it in the simplest form here now rather than the spinor notation. What you have to do is add a term. I know the term I'm going to add is sort of controversial, but hopefully by the end of my talk it will not be. So you simply add a term that breaks the fact that if you were to go to the chemical potential, you wouldn't have the Z2 symmetry. The simplest term that you can add is this. And there's a sum over P here. So it's the Hubbard model but in momentum space. And this causes all sorts of conniption fits by people, because this is inherently non-local in real space. But it's the simplest term from just this symmetry argument, and that's what I want you to focus on right now. I'll walk you through how you can think about this so it doesn't seem so unnatural. So this is the simplest term, and that term is odd under Z2. Now there's a way of thinking about this in terms of Landau terms. If you set P equal to P prime, if you wanted to do that, but yeah, this is odd under Z2. Now, for this to do anything to a Fermi liquid, it had better have a scaling dimension less than -1. Well, it does. When you count these, each fermion operator scaling dimension has scaling dimension 1/2. This -1/2. And then there's a tau and an S and an L integration. Those cancel out. There's only one momentum integration. There's one momentum integration. The scaling dimension is governed by the scaling dimension of the fermion operators. This is scaling dimension -2, which means it's a relevant perturbation to a Fermi liquid. Okay, this model was written down a long time ago. This analysis we did, and it wasn't pointed out that this fundamental thing about Z2 and the fact that it had a scaling dimension of -2, it was just written down as so it's a relevant interaction. This is what is known as the Hatsugai-Kimoto model. It has to define any fixed point. That's what I'm going to tell you about. And there's a precursor to this. Now, what's interesting is that this model, which in real space is an all-to-all interaction, was written down 6 months before SYK. But you never heard about it because people didn't take it seriously. But serious people, like Kunyan, are taking it seriously. Okay, so let me tell you about what this model means. Okay, so the general HK model stands for any model of this form. This term simply says you pay a penalty anytime 2 electrons go into the same momentum state. And this term completely commutes with that term. So K is still a valid quantum number. If U is large enough, if U is bigger than the bandwidth, then clearly you split putting 2 electrons into the same K state to such a large point that in fact you bifurcated the spectral weight into 2 pieces. And here is what one of the excitations looks like. This is the other one. And these weights depend on the occupancy. And if they depend on the occupancy, these are not electrons that you're putting into these states. This is the lower Hubbard band. This is the upper Hubbard band. I'll tell you exactly what these operators are. And you're getting all of, and since there are 2 of these, you can't write this as just 1 over a pole, and you will get zeros. Okay, so let me tell you what the band structure, why you get zeros. If you simply look at that expression and set the occupancy equal to 1/2, the real part of the retarded green function looks like this. And you can interpret this quantity. Let's just say it's something. It's not the self-energy, because the self-energy typically has a perturbative expansion around the non-interacting limit, which means it can't diverge if you call it the self-energy. But it turns out this quantity diverges. Okay, if you simply, but I did call it the self-energy. Okay, sorry, right. Well, I called it sigma, but I didn't. But
this is called the Freudian split.
Yeah. Sorry. Okay, so if you simply have omega equal to the energy of this band, this thing diverges. So it diverges on this locus of points in momentum space, where this frequency equals this. Okay, which means this is equal to infinity, which means 1 over infinity is 0. So you have zeros of the green function. Okay, so that's where they come from. You can interpret them as a divergence of the quantity that you put here if you just put this over 1 common denominator. Okay, so there is no Fermi liquid quasi-particle anymore. and there isn't, because let's just look at this, okay? It does exactly what the Hubbard model was supposed to do. It gives you two bands. At each K, the spectral weight can either be here or up here. And there is a band of zeros. In this case, if the chemical potential lies halfway between these, that is symmetrical between this and this. The lower band is given by this operator, so it's a composite excitation, and the upper band by this operator. Okay, so everywhere along here, there are no electron excitations, and it's because there is this band of zeros. So if U is bigger than W, neither of these crosses the chemical potential, you get an insulator. And this is the Luttinger surface. Now, if you simply stick at n equals 1 and decrease the value of U, this band will dip below the chemical potential, and you'll see what starts to happen. The system will become a metal, because there are certain parts of the spectrum now which are singly occupied. So this region right here, from here to here, would be singly occupied. Well, the subscript here indicates how many excitations are there. So this is omega 0, omega 1, and this region right here, omega 2, this doubly occupied region. And now the surface of zeros is right here, only over the singly occupied part. So the surface of zeros keeps shrinking. So that's important when you go and calculate the Luttinger sum rule. Okay, which I do right now. Now, the simplest way to calculate the occupancy or the density in the system is just to calculate the total weight under the occupied part, which you just do from third grade math, just sum up the area here. But the more complicated way of doing that is count the number of times the real part of the green function changes sign. And it changes sign anytime any of these surfaces dips below here, which means there's a sign change here, 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 and there. So let's count those sign changes. And you simply add up the weights under those sign changes, and that is how you get the Luttinger sum rule. Okay, so what you want to do, and every time you change, it goes from positive to negative, or negative to positive, depending on how you started. Okay, so this is the actual, what the number should be. It should be twice the real part, the Heaviside step function. You simply count this has the positive quantity, you can simply weighting each sign change by a factor of 2. And what you see is that if this band of zeros symmetrically is symmetric around the chemical potential, then this weight will be twice, this weight right here is twice the weight of just this piece. It means you can put this here, and the whole thing will sum to exactly what it's supposed to. In which case, the naive way of counting is equal to counting the sign changes of the green function. But it doesn't have to be. This can just barely touch here, in which case this thing will not be symmetric around the chemical potential. As you see, twice this thing is not equal to this. And as a result, if you add up all the sign changes of the real part of the green function, you can't put this here and exhaust all the weight here. Some of this weight will be exhausted by zeros. Okay, now this, it turns out, will be relevant, and I'll show you in the next lecture, in defining topological invariance for interacting systems. And you'll see that this leads to a disconnect between these things called N3 and the Chern number. And it's the same sort of thing that's going on in the Luttinger count. The zeros are screwing you up.
What's N3?
Eduardo, you've now asked me that same question 7 times. Every time I go into your office, I tell you about N3, you go, what's N3? Okay, I'll tell you next time. N3, Does anyone know what N3 is?
Nobody knows what the answer
Okay. You take the trace, alpha, beta, gamma over 6, the integral over omega k x ky, and you have 3 derivatives. You have g inverse partial case of I, g.
Oh, that.
3 times. Every time I tell you, you say, oh, that. Okay? And then I can ask you in an hour, you say, N3, oh, what's that? Okay, so, you know, there was a talk by Kunyang on information. I won't say the next thing.
There's certain lack of information, but who calls it N3?
Volovic, Suchen Zhang, Gurari. It's the subscript is based on the number of factors of g inverse partial g that you have. So that's a mnemonic. Okay. So yeah, so you violate the Luttinger count, and it's very clear in this model because you can do all the calculations exactly. Okay, so here the Luttinger count does not equal this, and it's because you can't exhaust all of this weight by counting pole-like excitations. They're zeros. Okay, so if you look at the complete phase diagram of this model, it looks like this. In general, it's a non-Fermi liquid. You have a Mott insulator, and this is just the weight of n over the actual n. Okay, now this model is so simple, I should be able to tell exactly why it's a non-Fermi liquid. Well, here's the reason. In a Fermi liquid, every excited state you can get by simply applying creation operators 1 or 2 at a time to the ground state. Okay? This is a non-Fermi liquid, this has to break down. All of these excitations have a one-to-one mapping with states in the non-interacting system. That's not the case here. Okay, so if you look at this, I apply this operator because these are the things now which create the lower band. If I were to put 2 electrons, or 2, whatever these things are, these composite excitations, again, this one corresponds to this. How do I create this one? Well, I would have to apply this operator twice. But the problem is, this operator twice is 0, which means there's no way of getting this state if you want to stay in the lower band. You have to go to the upper band, which means that's the splintering of the spectral weight, in which case you are no longer adiabatically connected to the non-interacting system. And that's what's going on here. Okay, now, why should you care about this model? The singly occupied part is hugely degenerate. And you say, oh my goodness, this just violates all things I know about thermodynamics. As I said, people are beginning to take this model seriously. Serious people are, like Kugan.
I got yelled at, okay.
Yeah, I know you did, but those people don't know what they're talking about. Okay, okay, now.
We do.
Okay, so my colleague, Barry Bradlin, who was a postdoc here, is one of these people taking this model seriously because it allows you to make precise statements. And the question he asked is this degeneracy, which is in the band version of this HK model, something that is essential? And does it completely make all of the physics spurious? And the conclusion he came to is no. So here's what he did. So here's the HK model, and you have this band of zeros, and the degeneracy is 2 to the n. Now the reason why it has this huge degeneracy, it's because it's basically a version of the single site Hubbard model. So what Barry did is simply went to a 2 orbital basis, and the 2 orbital basis, it's the Hubbard dimer. The degeneracy goes away for the Hubbard dimer. And as a result, but the zeros don't go away, which means the splintering of the spectral weight into these 2 pieces and everything I just told you still holds without the degeneracy. Okay, and as a result, none of that is crucial. Okay? Okay, so it's in this sense then that you should think about this model degeneracy is not a real problem, and you still get the zeros, which is the non-zero feature for obtaining Mott physics. Okay, now, I've thrown away a lot in just writing down this HK term. Let's ask the question, if I were to add in anything local, do I go away from HK physics, which is defined by an operator that has scaling dimension -2? Okay, so does it survive these kinds of perturbations? Okay, so what you want to do is RG, and you want to do RG around each of these surfaces now that defines the fillings in this model. Okay, so you sometimes you have two, sometimes you have one, but you want to RG in the most complicated case. You can go and do this. And so you can linearize the dispersion around here and here. And if you do that, if you just do tree level scaling with this 4 fermion term, this 4 fermion operator term, 2 fermion term, these are the scalings. At tree level, they're all irrelevant. You can go to one loop and do the calculation. You can calculate the beta function forward scattering, it's equal to 0. And it's because all of this is just less relevant. The only thing that is relevant is superconductivity. Okay? So there's nothing local that you can add to go and destroy HK physics. Okay, and part of the reason for that is the fact that HK still preserves K as a quantum number. Okay, so beta V local is equal to 0. This thing diverges, but the question is, what kind of superconductivity do you end up with? And that's going to be the second half of the talk. Okay, so this is telling you there's a quartic stable fixed point. Okay, so if you take Fermi liquid theory, rather than approaching with the jackhammer, you just break it up with the Z2 symmetry breaking operator. And what it does is it splits the spectral weight into 2 pieces, which is what we were trying to understand in a controlled way, in which you can do all of the calculations exactly. Okay, now with this background, I want to now go and do the Cooper problem. I want to put in an operator that has to do with pairing. I don't care where it came from. There are enough people who seem to know where the pairing operator comes from. Let's just go and assume it's there and go and redo Cooper's problem, but not for Fermi liquid, but for the HK problem. Okay, so I put this onto HK, not a Fermi liquid, and I simply go and calculate this energy difference. And if there is an instability, EV should be negative. And in fact, it is. And this is the leading order of the instability for the pair binding energy. Okay, now the more interesting thing, as in a Fermi liquid, you can go and calculate the pair susceptibility exactly. You can also do that here. So this is the quantity you have to go and calculate. And because of the structure of it, it looks just like this. But chi0 is not the chi0 for Fermi liquid, it's for HK. Okay, and if you do that, then when this thing is equal to 1, that will define TC. So this calculation can be done exactly. Edwin Huang did it exactly. And this is the behavior of chi0, and it just grows. And once this crosses 1 over G, you'll end up with a superconductor. And that's what happens right here. So that you define, so the TC can be defined as where the susceptibility diverges. Okay, and so TC will end up looking something like this, and note the form of this exponent. Okay, now what one would, so this is an exact calculation. What you'd like to do is do what BCS did, write down a wave function for the superconducting state. Okay, now in BCS, it's a fairly simple problem because you either have things which are completely occupied or empty. So this would be empty, this would be completely occupied. But that's not what is exactly going on here. In this problem, but note something. You can take this BCS wave function and just limit yourself to positive k, and then note there are three distinct terms that you can write down in the wave function. Okay? Now, this is just a little heuristic to tell you that there are three parameters, but they're all related. Okay, now, this helps you understand, right, okay. So if you look at the HK model, there are three different occupancies. And you can redo this for Barry's two-orbital model, and you'll still end up with the same thing, no essential details change. Okay, so the generalization now is that there are three parameters in this wave function, because there are three distinct occupancies, and it's the singly occupied part that gives rise to the new non-Fermi liquid physics. Okay, so there are three parameters, and you can go and solve the equations, the self-consistent equations that you end up with. This defines the singly occupied part, W, and this empty. Okay, so you now have to, this is your normalization condition. And the key thing about any sorts of variational wave functions of this sort is you define a gap equation. You can do that, and the gap will have this sort of exponent, which is different from the one that appeared in TC. Okay. In BCS, they're the same. Okay, so this is sort of a curious result. But the other thing that you can do, since this is at this level of the wave function, you know the complete spectrum, you can easily go and calculate the free energy. So if you calculate the free energy, each of these is at a different temperature as a function of the gap, which might open over delta zero. What you find is at high enough temperature, there's only one minimum right here. So this is T above, some larger temperature. But there is a temperature at which you find that there are two degenerate minima, and there's a non-zero value for the gap. And it's degenerate with the case where there's no gap. Okay, and then as you decrease the temperature even further, this minimum goes to higher values of delta, and that's T less than TP. And there is a unique minimum in this system. And the part where the temperature which the free energy has a unique minimum is identically equal to the temperature in which the susceptibility diverges. Okay, now this sort of behavior would indicate that it's unclear how you define really what TC is. It seems like really it's just the pairing temperature. It also seemed like it's a first order transition. Yeah, okay.
It's the other transition is preempted.
Yeah. Okay, so we were puzzled by this. As I said, we aren't the only ones. This cat's out of the bag once we revived this model from 1992. And and then, so this ratio is actually going off to infinity. There have been other papers looking at the same thing, and they all got the conclusion that we got, that in fact, if you look at the free energy, it seems as if this is a model in which this superconducting transition seems to be first order. And it's coming about from the strong correlations. Okay? Okay, so I don't want to go through all the papers that are doing this, but there are many now. Okay, now it's not just the way that we did this, there's no form factor that we added. You can put in a form factor to get other angular momentum pairing states if you want. I don't think that's particularly meaningful. all of them will have this sort of multi-gap type solution, and hence give you a first order transition. Okay, now why is it coming across this way that it seems to be a first order transition? You can parameterize the free energy the way that Landau did in terms of these parameters A, B, and C. And what you find is, and these parameters will in fact be momentum dependent. Okay, now if you look at the occupancy, 2, 1, and 0, as a function of K, it turns out, and if you simply look at what is going on in the standard BCS picture, this is what you have. This thing is entirely negative here. Okay, and this one, B, is entirely positive. B is the coefficient of the quartic term, A is the coefficient of the quadratic term. Okay, so and this is the case, right. The key difference is that the B coefficient, the coefficient of the phi to the fourth term, is largely negative as a result of the singly occupied part, the thing that gives you Mott physics. And it's exactly what the other people have noticed. It's the it's the stuff that makes this a non-Fermi liquid that's still being preserved in the superconducting state. Okay, and as a result, the complete theory would have to have a sixth order term. Okay. Okay, now, there seems to be a tricritical point, and you can define all of these quantities, but the key thing is that there's still a jump in the heat capacity. Even in this kind of transition, the heat capacity will at least will differ between the two phases, and here's what you have.
Don't you get the latent heat instead?
There will be a latent heat, but there's also a jump in the heat capacity. Yeah, right. Okay, and I don't know if people have looked for latent heat. It's why I asked you this cryptic question one day, and you said, well, of course, anyway.
Experimentally?
Yeah, experimentally.
Experimental transition is an XY transition. It has been measured with great accuracy.
Okay. Great accuracy to those
Great
who
accuracy.
think it's
No
accurate.
part
Okay.
to the part.
Is that exact or a rigorous statement?
No, it's an experiment.
Okay. So let's look at the condensation energy. Okay. The condensation energy in BCS is always less than this quantity. Here's BCS. In this case, it can be bigger than that. Okay, and it's because you have these multiple surfaces which are contributing to the superconductivity. Okay, now you can't say you really have a theory unless you write down what the excited states are. Okay, and the excited states in BCS, you simply construct them by annihilating your superconducting state. We have a different wave function, but the things which annihilate these things in BCS are linear combinations of the basic excitations in a Fermi liquid. Okay, particles and holes, or particles and holes. Okay, we don't have that here. We start off with these Hubbard bands. And so the basic excitations look fundamentally differently. These are composite excitations. And the order of our names on the paper, we call these pions. And here they are. Okay, there are two of them, one for the lower band and for the upper band. And they're in terms of the operators which create the lower band and the upper band. So nowhere does it simplify to these natural Bogolubov types of things. Okay, so the key point is that superconductivity is affecting both the upper band and the lower band. So normally in BCS, you simply just get this back bending right here, and this is identical to this. Okay, in this, you find features here and features up here. And note, this and this are not equal. That's because you've broken the particle hole symmetry. Yeah, this is the pion band. Okay, now why is this significant? It's significant because there are these, so we have stuff going on both at high energies and at low energies in the superconducting state. One of the features which I always puzzle over is this color change of that is inherent, that seems to be going on once the cuprates become superconducting. And this is Dirk van der Merel's experiment. So what they did is they simply integrated the spectral weight from a reasonably large value that would define what you mean by the low energy spectral weight. And omega, let's say, was 1,000 wave numbers. And a U is from the higher part is from that number to twice this value, namely the upper Hubbard band. Okay, and you're integrating now the optical conductivity from 0 up to this cutoff. So integrals of the optical conductivity with the correct weights should give you the number of carriers in the system. So an estimate of the superfluid density, as it were. Okay. Okay, and what they found is the following: that as the system goes through the superconducting transition, right here, the spectral weight in the lower band accelerates downwards, whereas the one in the upper band accelerates downwards, whereas the one in the upper band has a steeper rise. So there is a net transfer of spectral weight induced by superconductivity from high to low energies. Now, superconductivity should be entirely a low energy property. Well, this is telling you there's still something going on that's tethering the upper band to the lower band when the system superconducts. So there's still Mott physics going on in the superconducting state. Okay, now we can't calculate the optical conductivity because there's no scattering. We'd have to add various terms. But one thing we can calculate is the total weight in the lower band versus the total weight in the upper band as the system undergoes a superconducting transition. Now, why are we even focused on this? Well, the experimentalists told us this is important. Now, this ratio, this change in the spectral weight versus the nascent value is around 3%. But that small number, they said, is sufficient to explain the condensation energy. Okay? So this transfer of spectral weight from high to low energies, they say, is related to the condensation energy in this problem, which means you can't understand it without this mixing. Okay, so what we did is, since we have the wave function, we have all the eigenstates, we can actually go and do the calculation. We simply just calculated the total weight in the lower band as a function of the pairing interaction. And here's what we found. So this is this number, WL, the total weight in the lower band is a function of G, over the weight in the lower band when G is equal to 0. And this quantity is bigger than 1. The thing starts off at 1, which is good, and it just increases. And this is a function of G. Okay, and we're also increasing the value of U over T. So each of these is becoming smaller as you increase U over T. And when you include the pairing interaction, the nice commutativity that is present in the HK model between the kinetic and the potential term is lost. And hence there's dynamical spectral weight transfer. And it's that dynamical spectral weight transfer that's giving rise to this mixing between the upper and the lower bands. strictly the HK model, there's only a static spectral weight transfer. It does not depend on T. Okay, so let's look at a reasonable value for the, this looks somewhere right here. This weight, is roughly between 2 to 3%. So for reasonable values of we don't know what a reasonable value of this is. I mean, it might be that the Coop rates are down here, or they're up here. I don't know, but I'm just saying that it's illustrative to see that in fact you can get something. These numbers aren't like 85%, they're relatively small numbers. Okay, so why is there this mixing going on? Well, it's going on because of what I told you. This term and this no longer commute. And this dynamical mixing is giving rise to exactly the physics that you expect if you're seeing an integrated spectral weight at high energy going down and the one low energy is going up. Okay, that's exactly what goes on. That's what's seen widely in the Coop-Rate phase diagram, if you look at the initial studies of the optical conductivity. Okay. Okay, so this is dynamical spectral weight transfer. We think this is the general mechanism of this, but there is no other calculation, so I don't know anything to compare this to, because you need the high energy scale in the problem if you're going to obtain this effect. Okay, the last thing that I want to mention is the superfluid density. You can go and calculate this thing exactly, and well, within this wave function, and that's ds right here. And a Fermi liquid, it looks like this. It's the band insulator, and when the system is empty, you should have no superfluid density. It has to peak somewhere in the middle. These are just as you increase the value of the coupling constant. Okay, good. Now, for a Mott system at half filling, this has to drop to 0. So which means you all know what it has to look like. Okay, it has to look like these two smaller suppressed arcs. Okay. And then if you look at changing G, what you find is that there's a suppression of the superfluid density relative to the Fermi liquid case, and this is entirely induced by Mott physics. Okay, you can calculate the phase diagram. This is what you end up with. Now, everything that BCS can go and calculate, we can go and calculate. So here's the Hubble-Schlichter peak. There is none. Or at least it's, yeah, u equals 0. It's strongly suppressed for any reasonable value of u. Okay, rather than just going and cataloging all of these, telling what each of these things is, let me just look at the comparison. So here are some observables that you get in the superconducting state. And here's what you get for Fermi liquid theory. This is what you get from Mottness, when you split the spectral wave into two pieces and then go and solve the Cooper problem from that. Things look very different. So the susceptibility, the divergence of the susceptibility is different from where the pairing seems to occur. And the excitations are no longer these things which live on a Fermi surface, but they're these things that live on these Hubbard bands. And that's giving rise to all of the non-trivial physics. It's been pointed out before that there is no Hubble-Schlichter peak. That's what's seen experimentally, but the reasons for that are things like antiferromagnetism. What we're saying is that it's just coming from the Mott physics. It's just coming from you, the splintering of the spectral wave. Right, so these things look very different, okay? Okay, so that's what I wanted to say. So what I've shown is that if you use the HK model, and then you do what RG tells you to do, you simply ask the question, what are the relevant, what perturbations take you away from this point? We haven't been able to identify any, except superconductivity. And the superconductor that it's flowing to is not the BCS superconductor. It is, as our names are on the two Nature Physics papers that showed this, is a PYHZ superconductor. Okay. And it seems as if nothing local destroys it. Even if you were to add in the Hubbard interaction, you wouldn't destroy this. Okay. So let me just end with this. We understand the Fermi gas. We understand the Fermi liquid. Nice excitations. These things all pair up and you get a BCS superconductor. The terminus of this evolution is Sir Neville Mott. And the key point is the singly occupied part. And the singly occupied part does all of the work in making this a non-Fermi liquid. And all of the odd properties that I've told you about come about entirely for that. The way that the flow of the RG doesn't give you the same kinds of flows that you did in a Fermi liquid is entirely because of this part. Okay, I think that was it.
Yes. Thank you very much for the talk. If you started with the local interactions, have you found any examples where you can flow to the kind of non-local interactions you require?
Yeah. That's really what I'll talk about. Okay, so yes, I would say that if you're an electron in the Hubbard model, let's say you were, okay, and you're trying to get away from this site that you're on, you'd have to explore your neighboring sites. Are you the only electron doing that? All the other electrons are doing that. So in a sense, there is a long-range interaction even in the Hubbard model. Eduardo was shaking his head, but it's true.
This is not true.
Okay.
I mean, the question was, if you start with a theory with local interactions defined on a lattice, do you evolve at low energies to something like the HK model? And I think the answer is no.
Well, I don't know if that's true or not. So what I will do is, okay, I don't know if this is true or not, okay? But what I will show you tomorrow is the following. You go and solve the Hubbard model, and then you go and do the HK model in a really non-trivial system, and you get the same answer.
Even in one dimension? Where you can solve the Hubbard model exactly?
Well, look, you can't get the spectral function out exactly. You and I both.
Yes, you can. You have to use the four factors.
Yeah, but you've seen those papers. They're unintelligible.
Well, that is not to say that you cannot do it.
Yeah, you can do it formally, but you know other things formally.
You can calculate it.
Okay, so
I cannot do it, but they can.
Okay, so that defines what we know then.
No, it is not.
Okay, so look, my point is, the key thing about Hubbard physics is that this bifurcation of the spectral weight. And I think as long as that's what if that's the essential thing, I don't see any way of putting that back together again. I mean, local interactions they don't seem to flow you away from that. Okay, so if you start with HK, you add on local interactions, there's nothing that flows you away from that. You know, your point is, what about you start from the other point? Do you flow into this? Okay, well, I'll show you something tomorrow.
Can you go a couple of transparency parts where you have the superfluid density?
Right.
No, the two, the two thumbs.
Yeah, right here.
Okay, I'm going to ask you an unfair question. It's okay. So people have measured the superfluid density in the couplets.
Right.
Can you do an analog of this? Are you going to say that the superfluid density incorporates in some dimensionless form? So you have to define some ratio to make sense of this. It's smaller than that in a conventional low temperature superconductor. I think the answer is no. Right? You're going to say here that in this theory, the superfluid density in this model is necessarily smaller.
Yes, that is what we're.
And a high temperature superconductor presumably is going to have a larger one.
Well,
but you have to be careful. You have to measure.
Yeah, you have to.
You need a dimensionless version.
Yeah, it's some dimensionless version, and there is a lot of talk in Bozovich's papers on the suppression of the superfluid density relative to the Fermi liquid.
Yeah, but the question is,
so that you can't really compare these two in that way.
The question, otherwise you're saying here that your superconductor is a weaker superconductor than BCS.
Well,
and the answer is a high.
That's not true, because you see, we have a larger condensation energy. Okay. Okay, there's a larger condensation energy. Okay. So, but right, absolute comparisons aren't really possible, I would have to say.
Any other questions?
You're saying this is a non-Fermi liquid.
Right.
In addition to the Mott, do you observe other characteristics usually associated with non-Fermi liquids, like T-linear resistivity? I guess you don't have.
As I mentioned, we can't calculate any.
Even if you include like non-forward scattering on the Fermi surface or impurities.
Okay. Okay.
Well, you can calculate the electron, the self energy that you don't want to go.
Yeah, we can do that. Yeah, well, okay, yeah, but it doesn't have anything that you want, like omega to the 2/3 or something like this. Well, but that's well, you're in love with pneumaticity, Eduardo. Yes. You know it, I know it, all the American people know it, okay? So,
theory,
well, but I don't do perturbation theory. Okay, so.
I don't know what the answer is.
Okay, yeah, so we can, if you wanted to calculate an effective mass, okay, and you would see that diverging because the self-energy, okay, along the Lagrange surface, you can certainly go and do that. Now, this issue of the conductivity, okay, we would have to add in terms that have momentum, that have two different momenta, to get any sort of relaxation of the momentum. Okay, and we're in the process of doing that. That's one of the things Jin Xiao is supposed to do for his thesis. But let me tell you something, okay? So let me just tell you something. This I can write down, is that right? Okay. We were very excited about the following results, okay? We thought we had a slick way of getting T-linear resistivity.
No, I don't think so.
I said we thought we had a slick way, okay? Because you said, is there any way? Okay, so let me just tell you something that we were trying to do, that we thought we had done, but it's absolutely wrong. But I think.
Yeah, why are you still talking about it?
There are these ideas you have that are just so. No, let me just tell you what it was, okay?
It destroys the phase-space argument, so please don't.
Okay, Jin-Chao, you can leave the room. Okay. Your students keep you honest, like you're. And he's an extremely honest guy. Okay. Okay, so in Fermi liquid theory, the reason why you get T linear is that, T squared, is the phase space argument, right?
Sure.
Okay, so it's just the width of this thing that gets squared. There are 2 degrees of freedom, so it's squared. It's the width of the, actually it's not this one, it's this one. Okay, right. This width here is KT,
Yes.
okay, and KBT squared, okay? So the scattering rate should go as T squared, okay? But in this problem, there's an extra region which is not thermally broadened. It's this part here that's singly occupied. Okay? So what if you simply say that omega goes to KT You see the point?
No. Can you calculate that?
We just take the square, just square this plus this. There's a T squared part. This times this will give you a T linear part, because this is independent of temperature.
But that's not the calculation. You said, what if I write this?
Yeah, that's right. Okay, so then we thought we were doing, so in other words, the question we asked is, what is the momentum distribution function, the effective momentum distribution function that describes something that looks like this? And what is new about T-linear resistivity is that there are effective excitations that have a new momentum distribution function. And their effective momentum distribution in K-space looks like this. Okay, so we thought we'd done that, but it turns out that was, and then the physics of it would be essentially this, that this part is not thermally broad. You get these two regions here, and just simply square this, and you see there's a T linear part to the effective scattering rate. Okay, that was wrong. Okay, so erase that from the record. That's as far as we got. We are now adding systematically K prime, figuring out what are the relevant Ks that we need to add, like pi over 2, and see what happens to the scattering rate in those cases. But you see, that program is the sort of thing we don't like, because all of those terms are equally relevant. So let's say you got something, you couldn't say it was the answer. So it's still something we're pursuing. It's a work in progress. I don't know what the answer is.
So you mentioned the local interactions are RG relevant.
Right.
Impurities are, I believe, RG marginal in
Right.
Are they still marginal?
We haven't looked at that, so right.
There are two fermion operators in the impurity term, right?
Yeah, but they don't conserve momentum.
Right.
So they scale differently than the
Correct.
interaction.
Correct.
Yeah, so that means you'd have two integrations over momentum. And I think any time you do that, the relevance goes.
It's probably a marginal term.
It's a marginal term. It's a marginal term. So we'd have to go and do the calculation, okay? And I don't know what you'd end up with.
Okay, so let's thank Professor Phillips for his